Great to be back. We've been talking about strong induction, and in this new video I will be talking about strong induction but applied on computational geometry. It's a special application of strong induction, and let's have a look what this is all about. First of all, we have to look at some definitions. What is computational geometry about? First of all, it's a part of discrete mathematics, and in that part we study problems related to geometric forms or objects. It is very important when we look into computer graphics, computer games, robotics, scientific calculations, and many other areas. It's an area that is in fact essential to what we are doing today in IT. Now, when we look at the problems related to computational geometry, it's very important to define certain terms that in fact are necessary to understand what we will be talking about in the following slides. We have to look at some definitions related to geometric forms. First of all, we have to define what is a polygon. A polygon is basically a closed geometric figure consisting of a number of line segments, which we call sides, and the last side and the first side meet in a common endpoint, and we call that endpoint a vertex. Now, when we look at a simple polygon is a special type of polygon where no two non-consecutive sides intersect. So we have connections from side to side, and let's have a look at some examples later. Now, when we look at the interior and the exterior of a polygon, when we have a simple polygon, we have a kind of geometric figure that divides the plane in which it has been drawn in what we call an internal and an external region. The interior of the polygon is the part which is within the lines of the polygon, and the exterior is the part outside of the lines of the polygon. It will be clearer when we look at some examples of polygons. Now, let's continue with the definition. Let's say that a convex polygon is a polygon where every line segment connecting 2 points in the interior of the polygon lies completely in the interior. So basically, when we connect the points of the polygon, that connection, that line segment, is completely in or within the interior of the polygon. We have a non-convex polygon, which is basically a polygon which is not convex. So there are connecting lines that cross the connecting lines of the polygon and lie partly outside of the polygon. We will look into some examples like that. So let's have a look at some examples of convex and non-convex polygons. First, we have a triangle. This is clearly a convex polygon because all the line segments connecting the 2 points of the interior of the polygon, they lie completely in the interior of the triangle. Here we have a octagonal. We have the same, it's a convex polygon. We have a parallelogram, which is also a convex polygon. Now we have two non-convex polygons. We have some crazy form polygon, and we have the star-shaped polygon. So both of them are in fact non-convex polygons because we can connect some points of the outside, and that connecting line is going outside of the polygon itself. We will look into that in some other examples. Now, what is a diagonal? The diagonal of a simple polygon is a line segment connecting two non-consecutive vertices. So let's have a look what it can be. We have the internal diagonal, which is a diagonal which lies completely within the inside of the polygon. And we will see that all internal diagonals, or all diagonals when we have a convex polygon, are basically interior diagonals. Let's have a look at the diagonals and the triangulation of those different polygons. We look here at the triangle. We cannot draw any diagonals because they're the connecting lines, because we only have 3 vertices, so all is connected. We have the octagonal, and here we have some examples of diagonals starting from one point. We have the non-convex polygon, and we see that we have some internal diagonals and also some external diagonals. And basically we have the star also with internal and external diagonals. The thing we're going to look at is what we call triangulation. And triangulation is dividing simple polygons into triangles by adding non-intersecting diagonals. So we have to look at those diagonals, and they cannot be intersecting. Now, first of all, we have the octagonal. So we have those 8 corners, and we can connect the different diagonals, where I already find 4 triangles, and I find 6 triangles in total by adding this 5th non-intersecting diagonal. Now we can look at the non-convex polygon, and we can look at 2 possibilities. Let's have a look at the first set of triangles that we can make. So basically, this is a first possibility of triangulation of this non-convex polygon. We can do another triangulation with the red lines of the same polygon, creating different set of triangles. So basically, this is the principle of diagonals and of triangulation. Let's have a look at what we call the triangulation theorem and the accompanying lemma. The triangulation theorem states that a simple polygon with n sides, with n larger than or equal to 3, can be triangulated into n-2 triangles. There is also a lemma about triangulation, which says that every simple polygon with at least 4 sides has an interior diagonal. Now we have to look at those elements, because we are going to use the lemma to prove the triangulation theorem. Here we have a triangle. Well, we have 3 sides. We can find n-2 triangles. It means 1 triangle. The fact that we have 3 sides only means that the polygon itself is a triangle. When I have the octagonal, we find here we have 8 sides and we find 6 triangles. And in the last one, we can find a similar element. We can find the number of triangles. Now for the lemma, every simple polygon with at least 4 sides has an interior diagonal. Of course, the triangle has only 3 sides, so there is no interior diagonal. But we see for the other polynomials, we can see that there is, of course, at least 1 interior diagonal, which we can conclude because we've seen all those interior diagonals in those figures. Let's start by proving the theorem. The triangulation theorem says that a simple polygon with n sides, with n larger or equal than 3, can be triangulated into n-2 triangles. In order to prove this, we will use the lemma that I introduced before, and it's basically, when you look at it, a very simple lemma, but don't be let's say, confused by its simplicity, but it's very difficult to prove this in a general way. Now, we're not going to prove this lemma. It already has been done before. We will be assuming that the lemma has been proven and that we can use it within the triangulation theorem. We will use the proof by strong induction, and we will prove that the statement T of n is every single polygon with n sides and n is larger or equal than 3 can be triangulated in n-2 triangles. We will start from n equal to 3 because it is impossible to construct a polygon when n is smaller than 3. It's quite clear when we only have 2 corners, we have a line, and we only can draw a polygon from the moment that we have 3 vertices. The basis step is basically true. T of 3 is true since a polygon with 3 sides on its own is a triangle, and we can triangulate this polygon is n-2, is 3 minus 2 is one triangle. Basically, it's already triangulated on itself because it's a triangle. Let's now continue by proving the inductive step. The inductive hypothesis is that we assume that T of j is true for all integers j between 3 and k. And it can be translated as the statement that we can triangulate all polygons with sides j between 3 and k into j-2 triangles. Once we can prove this, we can also say that this is valid for k plus 1. Now, we have to assume that the inductive hypothesis is true. It means that we can accept that T of k plus 1 is true. It means that when we have a polygon with k plus 1 sides, we can in fact triangulate it into k plus 1 minus 2 is equal to k minus 1 triangles. So that's basically what the inductive hypothesis says. Let's have a look at the polygon with k plus 1 sides. It also means that k plus 1 is larger or equal than 4. Now we can conclude using the lemma that it has an interior diagonal AB which splits the polygon in two simple polygons Q and R. One, let's assume Q with S sides, and the other polygon R with T sides. Then we can say that the sides of R and Q are the sides of the original polygon P plus the diagonal AB, which is both a side of R and Q. Now we can continue this inductive step that we say that the sides of R and Q are the sides of the original polygon plus the diagonal AB, which is part of R and Q. That's the last step that I've shown on the previous slide. We have to note that S is between 3 and K, and the same for T, it's also between 3 and K, because Q and R have at least one side less than P. We can also state that the sides of P are equal to the sides of R plus Q minus 2, and we can say that K plus 1 is equal to S plus T minus 2. Using the inductive hypothesis, we can state that we can triangulate Q and R in respectively S minus 1 and T minus 1, since both comply with the conditions that they are between 3 and K, and consequently we can continue the triangulation to obtain S minus 2 plus T minus 2 is S plus T minus 4 is K plus 2 minus 2 triangles. Finally, this completes the proof by strong induction that a polygon with n larger or equal to 3 sides can be triangulated in n-2 triangles. So basically, using the proof by strong induction, we have proven that this theorem is true. And that's what we wanted to show you in this video. Now, in the next video, we're going to look at what we call the well-ordering property, and we are going to see that the well-ordering property and the mathematical induction and the strong induction are basically equivalent. So when we can prove anything using one of those proofs, the other proof will also be valid. Now you're doing a great job. I'm looking forward to seeing you in our next video. Thank you and bye-bye.